In this lecture, we will continue to look at the load introduction and discuss several design load cases for both aircraft and spacecraft. So how can we design the connection between the fuselage structure and the wing structure? There are several ways, and I will discuss two solutions with you to help you understand how important the design of load introduction into a structure is. We will take a closer look at the A400M airplane. You can see the aircraft in production without the wing installed on the left, and you can see the wing to be installed on it on the right. A cross-section of the airplane is shown for simplicity, together with the first solution to connect the wing to the fuselage structure. In this case, a clamped connection at the fuselage frames. This will introduce all the lift forces into the fuselage, but also all the bending deformation as a result of that lift. The frames will thus be highly loaded by tensional and torsional forces, so you will need very large and thick frames to carry all these forces. You can see that that is not a desirable solution. The second solution is a preferred solution and is applied on the A400M. It consists of a center wing box, which is shown on the right. The center wing box is designed in such a way that the normal forces introduced by the upper and lower wing skin due to wing bending are carried by the upper and lower skin of the center wing box. Only the lift is introduced into the fuselage structure as a vertical force by 4 attachment points. What we need to consider when designing the structures of an aircraft are all the loads that are acting on it and where they are mostly acting, if they are concentrated or distributed loads, and what the main design criteria are for the specific loaded areas. I will discuss the dominant load cases for the fuselage structure with you. First, we have the static ground loads. These can be quite significant, close to the landing gears. Then we have the downward bending of the fuselage due to the weight of the fuselage and wing structure, creating tensile stresses on top of the fuselage and compression at the bottom. We also have the pressurization of the fuselage, creating circumferential tension. So the dominant load cases for the top of the fuselage will be tension and fatigue. For the bottom of the fuselage, that will be compression, which will become critical instability. On the aft side of the fuselage, shear and fatigue loads will be dominant due to the empennage. The concepts and examples that I've shared with you so far to explain external loads, load paths, and load introduction were limited to static loads. There are also dynamic loads. When we look at fatigue or pressurization of the aircraft, although it is a cycling loading of the structure, it still can be considered as a quasi-static loading. But sometimes there are certain interaction of aerodynamic forces, structural elasticity, and inertia of the components, which may create oscillation of aircraft components. These oscillations may be quite significant and severe and need to be designed for. One example of this is flutter, which may lead to destruction of components by unstable vibrations. The design of aircraft structures needs to include damping properties of a structure to prevent this from happening. If the structure can dampen the oscillations, it will go back to its neutral state. If it is undampened, the structure will continue seeing these oscillations. And if this happens close to the natural frequency of the structure, it might even lead to divergent oscillation and cause destruction of the components. Until now, we have focused on aircraft load cases, but spacecraft are of course also subjected to several types of loading. They can be categorized in pre-launch loads, launch loads, and in-orbit loads. Before launching, the spacecraft experiences handling and transportation loads, as well as pre-testing loads. During launch, there are static and dynamic loads, such as shock loads and sine vibrations. When the spacecraft is in orbit, it will experience thermal stresses, internal pressure, among others. There are two main things to consider. Firstly, the direction of the loads. Loads can be directed in the axial direction of the launching vehicle, such as the thrust generated by the engine, or in the lateral direction, perpendicular to the axial direction, such as typical wind gusts or vehicle maneuvers. Secondly, the direction of the primary axis of the launching vehicle with respect to the primary axis of the spacecraft itself is important. As you can see in the picture, the primary axis of the spacecraft is perpendicular to the axis of maximum acceleration. If the primary axis of the spacecraft is parallel to the axis of maximum acceleration, you can imagine that it would yield a different design. What we have seen today is the importance of load introduction into a structure, and which different design loads spacecraft and aircraft need to be designed for.